These tracks only become useful when the chamber is placed inside a massive magnetic field. In this actual bubble chamber photograph, the field is what forces the particles into the distinct curves and spirals seen across the frame. The direction of a curve reveals the particle's electrical charge. Because of the magnetic field, positive particles are pushed one way, while negative particles curve in the opposite direction. By measuring the radius of these arcs, physicists can determine momentum. A high-energy particle will cut a nearly straight path, while a low-momentum particle is easily forced into a dramatic curve. As particles lose energy to the friction of the liquid, they lose the speed to fight the magnetic field, eventually collapsing into tight, inward-turning spirals. In many images, a disconnected V shape appears to begin out of nowhere. This indicates that an invisible, neutral particle, which leaves no bubbles, traveled through the liquid before decaying into two visible, charged particles. By converting these physical markings into coordinate data, researchers could finally determine the mass, charge, and lifespan of particles that were previously purely theoretical. The introduction of the bubble chamber at major accelerators led to an immediate surge in data. Instead of finding a few isolated anomalies, researchers began identifying hundreds of previously unknown subatomic entities. This handwritten ledger shows the scale of the change. Using chambers like Gargamel at CERN, physicists mapped out the lifetimes of strange particles, verified particle-antiparticle symmetry, and discovered neutral currents. The simplicity of the 1930s model was replaced by a reality so crowded that physicists began calling it the particle zoo. This overwhelming volume of evidence forced the scientific community to develop the Standard Model, a far more complex framework designed to bring order to the hundreds of new particles discovered in the bubbles. By the 1980s, bubble chambers were largely replaced by electronic detectors, capable of recording interactions at much higher rates. However, millions of the original photographs were archived without being fully analyzed. At the time, the manual labor required to measure every track was a mathematical impossibility. Today, researchers are digitizing these decades-old film reels and training artificial intelligence to scan the tracks. These algorithms are searching for rare decay patterns that were simply too subtle for human scanners to identify 50 years ago. While the boiling cameras of the 1950s have been dismantled, the records they left behind provided the evidentiary foundation for modern physics, offering the first clear look at a subatomic world that was far more populated than anyone had imagined.